All right, got a big heat transfer exam breathing down your neck? If the phrase volumetric radiation in cellular ceramics is giving you a headache, don't worry, you're in exactly the right place. We're going to cram the absolute most important stuff from a key research paper into just the next few minutes. Let's do this.
Oh yeah, we've all been there, right? Staring at some super dense textbook, the clock is just ticking away. My goal here isn't to read you the book. It's to pull out the absolute must-know takeaways that you'll actually need for your exam.
So for the next few minutes, we're going to break down a really foundational paper on this whole topic. Our mission is to take this kind of tangled mess of theory and turn it into clear, simple knowledge you can actually use on a test. So let's jump right in with the basics. Okay, listen up. Everything, and I mean everything in this paper, is built on just 3 core principles. If you can get these locked in your brain right now, I promise all the other details are going to make so much more sense. First, and this one is absolutely crucial, you've got to stop thinking about radiation as something that just hits the surface of an object. In porous materials, like these ceramic foams, heat is a volume problem. It's getting absorbed, it's getting emitted, and it's scattering all throughout the entire internal structure. Second principle, it all comes down to the geometry. Seriously, if you remember nothing else from this, remember these 3 parameters. Porosity, which is just how much empty space there is, the reflectivity of the solid material itself, and the pore size. Think of those as the 3 main control knobs for everything. And finally, number 3. How in the world do you do the math for something as complex and random as a foam? Well, you kind of cheat. You model one tiny representative building block, what's called a unit cell, and then you just assume the whole material is a giant stack of these. It's the only way to make the math even possible. So what does this unit cell thing actually look like? Well, the model the researchers came up with is actually pretty simple, and it's really the heart of their entire analysis.
And there it is. This simple shape, a cube with a hollow sphere inside, is the stand-in for that super complex, random structure of a real ceramic foam. It's designed to have an open, connected pore, just like the real material would. So this model really helps us nail down our key definition. Volumetric radiation is basically just the story of what happens to energy once it gets inside this unit cell. It's about all the interactions happening on those internal surfaces long before that energy ever finds its way out again.
You know, the best way to think about it is like a pinball machine. A photon of light enters the foam and boom! It's like a pinball. It's bouncing off the struts, it's getting absorbed, it's getting re-emitted, it's scattering all over the place. That chaotic journey inside the volume, that's what we're studying. Okay, so we've got the model. But what did it actually tell us? The paper lays out a few key findings, and these are the relationships you're absolutely going to want to remember for your exam. Now, don't get intimidated by the graph. It's simpler than it looks. Just focus on what it's showing us. On the bottom axis, we have porosity. Again, that's just the amount of empty space. And on the vertical axis, we have effective reflectance, how much radiation bounces back out. This is just connecting 2 of our key parameters. And here's the simple takeaway. The more open space you have, so the higher the porosity, the less the material reflects. It actually makes sense when you think about it. The radiation gets trapped inside all those nooks and crannies instead of bouncing straight back out. So more pores means less reflection. It's a simple inverse relationship. All right, let's move to the second key result. This graph uses a term that sounds really fancy, single scattering albedo. But all that means is, when energy hits something inside the foam, is it more likely to scatter or get absorbed? That's it. High albedo means more scattering, less absorbing. The takeaway here is just as clear. The more reflective the actual ceramic material is, the higher the albedo. This makes perfect sense, right? A material that's more like a mirror is going to scatter light way more effectively than a dull black material, which is just going to absorb it as heat. All right, you got the core principles and the key results. Let's do a quick knowledge check with a few questions pulled straight from the paper's conclusions. This is prime exam material here. First question, what are those 3 magic variables that control everything? I'll give you a second. If you said porosity, material reflectivity, and pore size, you are exactly right. Okay, next up, if you increase the porosity of a ceramic, what happens to its ability to block radiation, what's called its extinction coefficient? Think about it. The extinction coefficient goes down. That's logical, right? More empty space makes it easier for radiation to pass through. All right, here's a trickier one. For a given porosity, does the size of the pores affect the single scattering albedo? The answer is No, the paper found that it's actually independent of the pore size, as long as the overall porosity stays the same.
And let's just end the review with the money quote, directly from the source. This is the sentence to remember. The radiation characteristics are determined by, say it with me, porosity, reflectivity, and the number of pores per inch. That's the core of this entire paper.
So let's leave you with this thought. You now know the dials an engineer can turn. So how would you do it? How would you tune the porosity, the reflectivity, and the pore size to create the perfect material for a high-efficiency radiant burner? That's where all this theory becomes reality. Now, go ace that exam.